Now let's see directed graph. A directed graph or a digraph. G is a triple consisting of a vertex set V of G and an edge set E of G, and the function assigning each edge an ordered pair of vertices. So what they are trying to say is that we have triple. One is V of G, which is nothing but the set of all vertices, and the other one is E of G, which is nothing but the set of all edges, and there is a function assigning each edge to an ordered pair, which means it is going to say what is the tail and what is the head of the each edge, right? There should be a function which should say that. If you have all these three, then such a graph is called as ordered graph, right? So the first vertex of the ordered pair is the tail of the edge, and the second is called the head. So what I mean to say is, if you look at this example, it will be clear. Now this is going to have two. One is vertex set and other is edge set, right? Now let us say the vertex set is containing 1, 2, 3, 4. 1, 2, 3, 4 vertices, and the edge set is containing 4 edges. So what are the 4 edges? A, B, C, D. Now if you see edge A is having a mapping from this edge to the ordered pair 1, 2. What does it represent? That the edge is starting at 1 and ending at 2. So that is why this is called as tail and this is called as head. So starting at 1 and ending at 2, right? And similarly edge C is starting at 3 and ending at 4. Starting at 3 and ending at 4, right? Similarly edge B is starting at 3 and ending at 2. Starting at 3 and ending at 2. Got it? Similarly edge D is starting at 4 and ending at 1, right? Okay, now here also we can say that in case of directed graph also we can say that it is either simple or multi-graph. So what is a simple graph is, if we don't have any loops and multi edges, then we can say that it is a simple graph, simple directed graph. Now what I mean by a loop is, if the head and tail of a directed edge is same, then that is called as a loop. So which means if I have, let us say if we have a graph like this, okay, and now if I have a edge like this, then this is a loop. Now if you have such a loop, then that is not a simple graph. That is one way, that is one condition. And the second condition is, there should not be any multi edges. So what is a multi edges? If you observe this, if I have two edges which have the same head and same tail, right, like this, then this is a multi edge. This is not allowed. But just be careful, if you have one edge this way and other edge this way, right, still this is a simple directed graph. But in case of undirected graphs, this is not a simple graph. But in case of directed graph, this is a simple graph. The reason is, we should have the same tail and same head in order to qualify as a multi-graph. Got it? Okay. Now let's see the definition of a path in case of directed graphs. A path is a simple digraph whose vertices can be linearly ordered so that there is an edge with tail U and head V if and only if V immediately follows U in the vertex ordering. So this is the definition, this is the textbook definition. If you want to understand what path is in simple terms, if you look at the graph, from this graph you choose a vertex. From that vertex you go to the next vertex only if it is a tail and the next vertex is a head. Once you are there in the next vertex, from there you go to the next vertex only if this is the tail and the next vertex is the head for an edge. Otherwise you cannot move. That is the meaning of it, right? So now if you observe it, from 1 to 2 we can go, because from 1 to 2 there is a vertex, there is an edge with 1 as the tail and 2 as the head. And from 2 to 3, let us assume that 2 to 3 we have this way, right? From 2 to 3 you can go, because 2 is the tail and 3 is the head, right? So 2 to 3 there is a edge. And now from 3 to 4 if you have to go, you should have like this, right? Let us assume that this is the way. Now from 1 to 2 I can go, 2 to 3 I can go, and 3 to 4 I can go. Therefore you can say that there is a path from 1 to 4. So when is this path possible? So you should start from a vertex and go to the next vertex only when this vertex is the tail and next vertex is the head. Now again, if you have to go from here to the next vertex, any vertex, this vertex should be the tail and that vertex should be the head, right? So that is how the ordering should be there. That is what they are saying. A path is a simple digraph whose vertices can be linearly ordered so that there is an edge with tail u and head v if and only if v immediately follows u in the vertex ordering, which means see this. Here v is immediately following u. Now there should be an edge there in such a way that this one is the tail and this one is the head. Then only you can put it in a path. Otherwise you cannot put it. Again you are putting 2 and 3 in the ordering, right? So what does it mean? There should be an edge there with 2 as the tail and 3 as the head. Yes, there is an edge. That is why you are able to put it here. And again you are able to put 3, 4. Why? Because there should be an edge in the graph in such a way that 3 is the tail and 4 is the head. That is what they are saying. Okay, fine. Let's see this. So we are now discussing the topic of connectedness. There are two ways we can say that a graph is connected, especially coming to the directed graph. If it is connected, then it is called as strongly connected. In case if the directed graph is not connected, but if the underlying graph, okay, before going ahead we shall see what an underlying graph is. The underlying graph of a digraph D is the graph capital G obtained by treating the edges of capital D as unordered pairs. So what it means is, if you have a digraph, now for every edge you just remove the directions. Now whatever you get, that is called as the underlying graph, right? So now why is it important is, even if the original digraph is not connected, sometimes this one will be connected, right? So what, first of all, let's talk about connectedness. So in this case, what is connectedness is similar to the definition which we have seen in the undirected case. If between every two pairs, between every two vertices, if there is an edge, then we can say that it is connected. But in this case, instead of saying between every two edges, you have to say for every ordered pair, right? So for example, if you want to see that this one is connected, there should be a directed path from one vertex to other vertex for every pair of vertices, right? Which means there should be a directed path from 1 to 2, 1 to 3, 1 to 4, right? So in this case you can see that there is a directed path from 1 to 2, 1 to 3, 1 to 4. But then there is no directed path from 2 to 1. Check this. 2, from 2 I cannot reach 1 whatever way I go. If I go here, I'll be ending here, right? So I cannot go that way. Therefore from 2 to 1 there is no directed path, and so we can say that it is not connected, right? But then if you see the undirected version of this graph, which means if I remove the directions and if I see the underlying graph, in this underlying graph it is connected, right? So such a graph is called as weakly connected graph. Now let's see the definition. A digraph is weakly connected if its underlying graph is connected. Got it? Which means this is connected but this one is not connected. Now a digraph is strongly connected if for each ordered pair u comma v vertices there is a path from u to v. So which means in this case, if there is a path from u to v for every pair, then we can say that it is strongly connected. Therefore this graph is not strongly connected but it is weakly connected. Got it? Now let's try to do a small modification to this graph and now check whether it is strongly connected or not. Let us assume that for the same graph instead of having the edge from 1 to 2, let us say I have the edge from 3 to 1, which means tail is 3 now and this one is head is 1. Okay, all the other things are same. Okay, now let's see whether it is strongly connected or not. So how can you check it? For every ordered pair you should check whether there is a path from that u to v, right? So from 1 to 2, yes. From 1 to 3, see, even though there is no direct edge, there is a path this way. And from 1 to 4, yes. Got it? And what about 2? From 2 to 1, yes, there is a path. And what about 2 to 3? 2 to 3, yes. What about 2 to 4? 2 to 4 I can go like this, go like this, go like this. Therefore there is a path, right? So what about 3? From 3 to 1, yes. From 3 to 2, from 3 to 2, yes. From 3 to 4, yes. And what about 4? From 4 to 1, yes. And from 4 to 2, yes. From 4 to 3, yes. So what can we say now? For every ordered pair is connected. Therefore this is strongly connected, right? So if a graph is strongly connected, if a digraph is strongly connected, then it is definitely weakly connected as well. But if a digraph is weakly connected, it need not be strongly connected. This is the example. See this? This is weakly connected, but it is not strongly connected, right? And now this is strongly connected, and therefore it will be weakly connected as well. So how can we say it? Now if you try to find out the underlying graph will be connected. Therefore it is weakly as well as strongly connected. Got it? Okay. Let's see this. Strong components. The strong components of a digraph are its maximum strong subgraphs. So what does it mean? Now if you observe this graph, it is a digraph, right? So even though this is a digraph, it need not be strongly connected. Only a part of it will be strongly connected. If you can identify that maximal part, that is called as a strong component. Got it? So in this graph, if you see this, only the vertices 2, 3, 6, 5 are strongly connected. So which means if you see between 2, 3, 6, 5, if we take any ordered pair, like if I take 2, 3, there will be a path from 2 to 3. And if I take 3, 2, there will be a path from 3 to 2. Right? And similarly, if you take 3, 6, there will be a path from 3 to 6 as well as 6 to 3, like that. So this is the maximal subgraph of this graph, which is strongly connected. That is called as a strong component. Got it? Okay. Now let V be a vertex. Okay, we are talking about the vertex degrees. So in case of undirected graphs, we have something called as the degree. But here in case of directed graphs, we have two types of degrees. One is in degree and the other one is out degree. Now vertex degrees, let V be a vertex in a digraph, then the out degree d plus of V is the number of edges with tail as V. So which means you can assume that there is a vertex V, then what is its out degree is number of edges going out of it. That is nothing but the out degree, right? So if a edge is going out of it, then definitely V is going to become its tail. Got it? Now what about the in degree? In degree is if you have a vertex, then the number of edges coming into it is nothing but the in degree. Got it? Now if an edge is coming into it, then what will this vertex become? The head of that edge, right? Now look at this. The in degree d minus of V is the number of edges with head as V minus, right? And now if you observe it, every edge is going to contribute 1 to some vertex as in degree and 1 to some vertex as out degree, which means if we have a edge here in directed graph, then it is going to add 1 to the in degree of this vertex as well as 1 to the out degree of this vertex. That is the meaning. That is that is how you can understand this rule. See this? Now if I add all the out degrees, then it is going to be equal to the number of edges. Why? Every edge is going to add 1 to this sum, right? And what about this one? If you add all the in degrees, then that will be equal to the number of edges, because every edge is going to add 1 to this sum. Got it? So unlike the earlier undirected case, in the earlier undirected case, you had taken the sum of degrees to be equal to 2 into E, but here you are taking in degree is equal to out degree is equal to E. Sum of in degree is equal to sum of out degree is equal to number of edges. Okay. Similarly, you can apply the concepts of minimum in degree and maximum in degree. So whenever you talk about minimum in degree and maximum in degree, you can apply the same way. So if this is the minimum in degree and if this is the maximum in degree, then what is the average in degree? So the average in degree equal to mod E by V, right? So minimum and maximum will be like this. This is the relation. and again this is the maximum out degree, sorry, minimum out degree, and this is the maximum out degree. Then what is the average out degree? Average out degree is again E by V. Now this relation is this like this. Got it? So anyway, we have seen such relations in even the underrated case and some problems on it. The same kind of problems can also be solved using these relations here. Okay, fine.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.